Have you ever stopped to wonder where yesterday actually went? Not what happened yesterday, not what you remember, but yesterday itself. Did it vanish from reality forever? Has it been erased from existence like words wiped from a blackboard? Or could it still exist somewhere, hidden in a way that our minds were never built to perceive? Every second that passes seems to disappear forever. We celebrate birthdays because another year is supposedly gone. We mourn because the past feels unreachable. We plan because the future seems unwritten. Our entire lives depend on the feeling that time flows in only one direction. But physics has been quietly questioning this assumption for more than a century. Some of the greatest scientists in history, including Albert Einstein, eventually came to believe that the distinction between past, present, and future might not be a fundamental feature of reality at all. That sounds impossible. You can remember yesterday, but not tomorrow. Ice melts, but melted water never spontaneously forms the exact same ice cube again. We grow older, never younger. Every experience seems to prove that time is moving forward, yet the equations governing planets, stars, galaxies, atoms, and even light itself often make no distinction between moving forward or backward through time. Nature may not experience time the way we do. If that's true, then an unsettling possibility emerges. Perhaps the past hasn't disappeared. Perhaps it is still there, not as a memory, not as information, but as a real part of the universe itself. And if that's true, then another question immediately follows. What exactly is happening right now? That question sounds simple, but modern physics struggles to answer it. Right now for you isn't necessarily right now for someone else. Even two observers moving relative to one another can disagree about which distant events are happening at this moment. The more deeply physicists explored the universe, the stranger this became. Eventually, they reached a startling conclusion. The universe might not possess a universal present at all. If there is no universal now, then what becomes of the past? To answer that, we first need to understand something so familiar that almost nobody ever questions: time itself. Not clocks, not calendars, not hours or years. Time. Humans experience time as a continuous flow. Every moment seems to emerge from the future, briefly become the present, and then immediately sink into the past. It feels like standing on the bank of a river watching the water endlessly pass by. This experience is so convincing that most civilizations throughout history accepted it without hesitation. Ancient astronomers measured the movement of the sun and stars. Farmers tracked the seasons. Civilizations built calendars. The invention of clocks made time measurable with astonishing precision. But measuring something is not the same as understanding what it is. Imagine explaining water without ever seeing molecules. For thousands of years, people could describe waves, rivers, rain, and oceans without knowing that water consists of countless microscopic particles. Time may be similar. We measure it constantly, yet its true nature remains surprisingly mysterious. Isaac Newton offered one of the first mathematical descriptions of time in the 17th century. For Newton, time existed independently of everything else. Whether planets moved or not, whether people existed or not, whether the universe contained galaxies or complete emptiness, time would continue flowing at exactly the same rate. Invisible, perfect, universal, like an enormous cosmic clock ticking identically everywhere. This idea worked extraordinarily well. Newton's laws predicted planetary motion with incredible accuracy. Engineers built machines. Astronomers calculated eclipses centuries in advance. The scientific revolution flourished because Newton's picture matched everyday experience almost perfectly. If two people owned perfect clocks, both clocks should always agree. A second would mean exactly the same thing throughout the universe. The past would be universally shared. The present would be universal. The future would arrive simultaneously for everyone. It seemed obvious. For over 200 years, almost no one questioned this picture. Then something unexpected happened. Scientists began studying light. Light refused to obey expectations. During the 19th century, physicists including James Clerk Maxwell united electricity and magnetism into one elegant mathematical framework. His equations predicted something remarkable. Light was an electromagnetic wave. Even more remarkable, those equations predicted one specific speed, about 299,792 kilometers every second. Notice something unusual. The equations never asked who was measuring, whether the source moved, whether the observer moved. The speed remained the same. This created a serious problem. Imagine standing on a train moving at 50 kilometers per hour. If you throw a ball forward at 20 kilometers per hour, someone standing beside the tracks measures the ball moving at 70 kilometers per hour. Everyday velocities simply add together. Physicists expected light to behave similarly, but Maxwell's equations refused to cooperate. If someone carried a flashlight aboard a rapidly moving spacecraft, should the light travel faster? The mathematics insisted no. The speed remained exactly the same. This wasn't merely surprising, it threatened the foundations of Newton's universe. Scientists searched for explanations. Many believed light must travel through an invisible substance filling all space. They called it the luminiferous ether. Just as sound needs air, perhaps light needed an invisible medium. If Earth moved through this ether, scientists should detect a tiny difference in light speed, depending on Earth's direction of travel. In 1887, Michelson and Edward Morley built one of history's most famous experiments. Its precision was astonishing for its time. They expected a small shift. Instead, nothing. No ether wind, no measurable difference. Light behaved exactly the same in every direction, again and again. The experiment was repeated with increasing precision. The result never changed. Nature appeared to be telling physicists something profoundly unexpected. The speed of light wasn't adapting to observers. Instead, reality itself might have to adapt to light. Almost nobody liked that conclusion. It sounded absurd. Yet one young patent clerk in Switzerland looked at the problem differently. Rather than changing Maxwell's equations, he wondered whether our understanding of space and time themselves might be wrong. His name was Albert Einstein. In 1905, during what historians now call his miracle year, Einstein published several papers that completely transformed modern physics. One of them introduced special relativity. Instead of assuming time was universal, Einstein proposed two deceptively simple principles. First, the laws of physics are identical for every observer moving at constant speed. Second, the speed of light in a vacuum is identical for every observer, regardless of how fast they move. Those assumptions sound harmless. They aren't. Together, they force reality into behaving in ways that completely contradict everyday intuition. If everyone measures the same speed of light, then something else must change instead. Distance can change, time can change, even simultaneity itself can change. The universe suddenly became stranger than anyone had imagined. And it is this discovery, not black holes, not quantum mechanics, not even the Big Bang, that begins to reshape our understanding of whether the past has truly disappeared. Imagine pausing the entire universe. Every star freezes, every planet stops in its orbit, every atom becomes perfectly still. If you could somehow step outside the universe and look at this frozen picture, what exactly would you see? Would you see only this single instant? Or would you somehow see every moment that has ever happened? Our intuition insists there must be only one current universe, one present, one cosmic snapshot. But whose snapshot? Suppose someone is standing here on Earth looking toward the Andromeda galaxy. At exactly the same moment, another observer flies past Earth at nearly the speed of light. Both observers occupy almost the same point in space. They even look in exactly the same direction. Yet, according to Einstein's relativity, they do not necessarily agree on what is happening in Andromeda right now. Think about that carefully. They are standing almost shoulder to shoulder. Neither is wrong, neither has a broken clock. Nature itself allows both descriptions to be correct. One observer may conclude that at this very moment, an advanced civilization inside Andromeda has already launched a spacecraft. The other observer concludes that launch has not yet happened. Neither observer is confused. This isn't an illusion caused by delayed light. Even after correcting for the travel time of light, they still disagree about what events belong to the present. This is called the relativity of simultaneity, and it is one of the most astonishing consequences of special relativity. Notice what just disappeared. Not the past, not the future, the present. Physics quietly removed the one thing we thought was unquestionably real. There is no universal cosmic clock announcing now. Instead, every observer slices spacetime differently. Each carries their own definition of the present. That should make us uncomfortable. If there is no universal present, then where exactly does the past end? Where does the future begin? Perhaps those boundaries never existed in the first place. This strange idea became even clearer when Einstein's former mathematics professor, Hermann Minkowski, looked at relativity from an entirely different perspective. In 1908, only 3 years after special relativity, he gave a lecture that forever changed physics. He said something historians still quote today. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a union of the two will preserve an independent reality. Those weren't poetic words, they were mathematics. Instead of imagining the universe as 3 dimensions of space through which time flows, Minkowski combined them into one 4-dimensional structure, space-time. Imagine drawing your life not as a moving person, but as a complete line. Your birth is one point. Your first day of school is another. Every heartbeat, every conversation, every sunrise you've witnessed, every mistake, every success, every future decision, all connected into one continuous path through spacetime. Physicists call this your world line. You never actually leave earlier parts of this line behind, you simply experience different locations along it. Think of a movie stored on a hard drive. When you watch it, the story unfolds one frame after another. It feels alive. Characters move, events happen, time appears to flow. But inside the computer, every frame already exists. The beginning hasn't vanished. The ending hasn't been created. All the frames coexist. Only the projector reveals them sequentially. Some physicists believe consciousness may work similarly, not creating time, experiencing it. Your brain could be moving through space-time much like a reader moves through the pages of a novel. The pages don't disappear after you've turned them. They remain exactly where they always were. Only your experience changes. This picture of reality is often called the block universe. Imagine the entire universe, not just today, but every moment from the birth of the cosmos nearly 13.8 billion years ago to the final fate of every galaxy. Not unfolding, simply existing, like an unimaginably enormous cosmic sculpture. Every dinosaur, every emperor, every child, every supernova, every black hole collision, every civilization that ever lived, every future generation, every star that has not yet ignited, all occupying different locations inside the same 4-dimensional structure. At first glance, this sounds almost mystical. It isn't. The idea arises naturally from Einstein's equations. In fact, many theoretical physicists argue that once you accept relativity completely, something like the block universe becomes surprisingly difficult to avoid. The philosopher Hermann Weyl, one of Einstein's closest intellectual companions, wrote something deeply unsettling. He said, "The objective world simply is. It does not happen." Read that sentence again. The universe does not happen. It simply exists. Our feeling that moments continuously come into being could be a feature of human consciousness rather than a property of reality itself. That possibility changes almost everything. Because if every event exists somewhere within spacetime, then asking whether the past still exists becomes almost like asking whether Paris still exists after you've flown to Tokyo. Of course it does. You simply aren't there anymore. But before we become too comfortable with this idea, another puzzle appears, one that seems to contradict everything we've just discussed. If every moment already exists, why do we remember only the past? Why don't we remember tomorrow? Why does broken glass always scatter across the floor instead of assembling itself back into a perfect drinking glass? Why does smoke spread through a room but never spontaneously gather back into a candle? Why does cream mix into coffee but never separate itself again? Every law of motion we've discussed so far is surprisingly indifferent to time's direction. Imagine recording two planets orbiting each other. Now play the video backward. Without any additional clues, Newton's equations work perfectly both ways. The planets obey exactly the same laws. The same is true for much of electromagnetism. Even Einstein's equations remain almost entirely symmetric with respect to time. So where does our powerful feeling that time only moves forward actually come from? The answer doesn't emerge from gravity, or relativity, or motion. Instead, it appears to emerge from something much more ordinary: disorder. At first glance, disorder sounds far too simple to explain one of the deepest mysteries in existence. Yet this simple idea became one of the most profound discoveries in all of science. And strangely enough, its origins begin not among the stars, but with steam engines. Imagine watching a video of the universe. Not just Earth, the entire universe. You press play, stars ignite, galaxies collide, black holes grow. Life appears on one small planet orbiting an ordinary yellow star. Civilizations rise, people laugh, cry, remember, and wonder. Now press rewind. Everything happens backwards. Ash gathers itself into burning wood. Broken mountains rebuild. Dead stars absorb their own light. Galaxies separate instead of merging. Eventually, the universe becomes younger, hotter, denser, until every atom disappears into the incredibly hot state we call the Big Bang. The remarkable thing is that for many of the fundamental laws of physics, both movies satisfy the equations. This surprises almost everyone. We instinctively believe that the laws of physics should somehow forbid the backward movie. But in many cases, they don't. Newton's equations work both ways. Maxwell's equations describing electromagnetism are almost perfectly time-symmetric. Einstein's special relativity and general relativity also make no preferred distinction between past and future. Even the Schrödinger equation, the fundamental equation of non-relativistic quantum mechanics, is time-reversible. This raises one of the deepest questions in modern science. If the laws don't care which direction time moves, why does the universe? Physicists call this the arrow of time. Notice the wording, not time itself, the arrow of time, because the mathematics often contains no arrow at all. The arrow seems to emerge from somewhere else. The search for that somewhere else eventually led physicists into an entirely different branch of science: thermodynamics. Ironically, one of the greatest clues about time wasn't discovered while studying stars. It emerged from engineers trying to build better steam engines. During the Industrial Revolution, scientists wanted to understand why no engine could ever be perfectly efficient. Why was some energy always wasted? Why couldn't every bit of heat become useful work? Among the people trying to answer these questions was the German physicist Rudolf Clausius. In 1865, Clausius introduced a new concept that would eventually reshape our understanding of time itself: entropy. Few scientific words have been misunderstood more than entropy. It is often described simply as disorder. That description isn't exactly wrong, but it is far too simplistic. Entropy is better understood as the number of microscopic arrangements that produce the same large-scale appearance. Imagine opening a brand new deck of playing cards. The cards are arranged in one very specific order, ace through king, every suit perfectly organized. Now shuffle the deck thoroughly. Nothing has been added, nothing has been removed. The same 52 cards still exist. But now there are approximately 80,655,170,943,666,766 sextillion, 289 septillion, 505 octillion, 440,000 nonillion, 883 decillion, 277 undecillion, 824 dudecillion, 1 trillion of possible arrangements. That number is unimaginably enormous. The ordered arrangement represents essentially one possibility. The shuffled arrangements represent almost all possibilities. The deck naturally moves toward the vastly more probable state. Not because nature prefers chaos, but because there are overwhelmingly more ways for the cards to be shuffled than perfectly ordered. Now replace cards with atoms. Your coffee cup contains roughly 10 to the 24 molecules. A tiny grain of sand contains trillions upon trillions of atoms. The air in your room contains numbers so large that even writing them becomes impractical. Every second, these particles move, collide, exchange energy, and change position billions of times. Yet somehow, your room doesn't suddenly become perfectly organized. It becomes less organized. Heat spreads, perfume diffuses, ice melts, stars burn their nuclear fuel. The reason is purely statistical. There are incomparably more microscopic arrangements corresponding to mixed than separated. This insight was transformed into mathematics by the Austrian physicist Ludwig Boltzmann. Boltzmann made one of the boldest claims of the 19th century. He argued that entropy wasn't just an engineering concept, it was statistical. Reality itself is governed by probability. His famous equation, S equals K ln W, is engraved on his tombstone in Vienna. Here, S represents entropy. K is now called Boltzmann's constant, one of the fundamental constants of nature. And W represents the number of microscopic configurations compatible with the same macroscopic state. At first glance, this equation seems almost innocent. In reality, it completely changes how we think about time. Suppose you drop a glass onto a stone floor. The glass shatters into hundreds of fragments. Could every fragment spontaneously jump back together? Surprisingly, the laws of motion don't forbid it. Every molecule could, in principle, reverse direction at exactly the right instant. Every collision could perfectly retrace itself. Every vibration could undo itself. The glass would rise from the floor completely intact. Physics allows it. Probability does not. The number of microscopic arrangements corresponding to a broken glass is astronomically larger than the single arrangement corresponding to an intact glass. The event isn't impossible, it is simply so unlikely that it would not occur even if the universe lasted vastly longer than its current age of approximately 13.8 billion years. This distinction matters enormously. Many people think physics says broken things cannot unbreak. That isn't true. Physics says the reverse process is unimaginably improbable. Already, something remarkable has happened. The direction of time is no longer emerging from Newton or Einstein or Maxwell. It is emerging from statistics. But this deepens the mystery. Statistics explains why entropy increases, yet it assumes something extraordinary from the very beginning. The universe must have started in an incredibly low entropy state. Think about that. The Big Bang is often imagined as a hot, chaotic explosion. That picture is misleading. It certainly was hot, but according to modern cosmology, it was also astonishingly ordered in a gravitational sense. This puzzled one of the greatest mathematical physicists of the 20th century, Sir Roger Penrose. Penrose realized something extraordinary. If gravity had been randomly distributed at the beginning of the universe, matter should have immediately collapsed into enormous black holes. Instead, the early universe was astonishingly smooth. Measurements of the cosmic microwave background, first by COBE, then WMAP, and with exquisite precision by the Planck satellite, show that only about 380,000 years after the Big Bang, temperature differences across the observable universe were only about 1 part in 100,000. That is an almost perfectly uniform universe. Tiny fluctuations, barely noticeable, would later become every galaxy, every cluster of galaxies, every star, every planet, and eventually every living creature that has ever existed. Roger Penrose calculated just how extraordinarily special this initial condition must have been. His estimate has become legendary. The probability of the universe beginning in such a low gravitational entropy state is roughly 1 part in 10 to the 10 to the 123rd. Not 10 to the 123, 10 raised to the power of 10 raised to the 123, a number so incomprehensibly vast that there are nowhere near enough atoms in the observable universe to write all of its zeros. Penrose himself remarked that this number is so enormous that ordinary language completely fails to describe it. And suddenly, our original question returns with even greater force. Perhaps the reason we remember the past, perhaps the reason galaxies evolve, perhaps the reason stars are born and die, perhaps the reason life itself can exist is because the universe began in one of the most extraordinarily special states imaginable. But that raises an even deeper mystery. Why did the universe begin in such an impossibly ordered state in the first place? Modern physics still has no accepted answer. Some physicists suspect the answer lies hidden inside quantum gravity. Others believe inflation somehow explains it. Others argue it may require an entirely new principle of nature. And until we answer that question, we may not truly understand whether the past is merely remembered or whether it remains a permanent part of reality itself. Let's imagine that tonight you step outside and look at the sky. At first, nothing seems unusual. Thousands of stars, a faint band of the Milky Way stretching across the darkness, perhaps a distant galaxy visible through a telescope. It feels as though you're simply observing the universe as it exists right now. But you're not. In fact, you have never seen the universe as it exists right now. Not once in your entire life. That statement sounds absurd, but according to physics, it is literally true. Everything you have ever seen has belonged to the past. Even the words you're hearing at this moment are already slightly old before your brain finishes processing them. Your eyes do not see reality directly. They see light, and light takes time to travel. Although the speed of light, 299,792,458 meters per second, is astonishingly fast, it is still finite. That single fact quietly changes everything. Look at the moon. The light entering your eyes tonight left the lunar surface about 1.3 seconds ago. You're seeing the moon as it was more than a second in the past. Look toward the sun. The sunlight warming your skin today began its journey approximately 8 minutes and 20 seconds earlier. If the sun were to vanish, a purely hypothetical thought experiment, we would continue seeing it in the sky for more than 8 minutes. Earth would also continue orbiting the location where the sun had been during that interval, because changes in the gravitational field also propagated the speed of light, according to general relativity. Already, something fascinating has happened. The present has slipped away again. The sun you see no longer exists in that exact state. It has already changed. Its nuclear fusion reactions have continued. Billions upon billions of hydrogen nuclei have fused into helium while their light was still traveling toward Earth. Now extend your gaze beyond our solar system. The nearest star beyond the Sun, Proxima Centauri, is about 4.24 light-years away. Its light began traveling toward Earth before many children entering primary school today were even born. Move farther still. The bright star Betelgeuse lies roughly 550 light-years away. When the photons entering your eyes left Betelgeuse, Europe was in the late Middle Ages. The Ottoman Empire had not yet reached its greatest expansion. Leonardo da Vinci had not yet painted the Mona Lisa. Everything that happened on Earth during those centuries occurred while those same photons silently crossed interstellar space. Suppose Betelgeuse exploded into a supernova tomorrow. Would we know? No. If it had actually exploded 100 years ago, we still wouldn't know. Its newest light simply hasn't reached us yet. Astronomers would continue seeing a perfectly ordinary star until the information finally arrived. This is one of the strangest consequences of the finite speed of light. Events don't become part of our observable universe when they occur. They become observable only when information reaches us. Physics places information at the center of reality. The universe doesn't instantly update itself across cosmic distances. Instead, every observer lives inside what might be called an information horizon. Beyond that horizon, events may have already happened, but their information has not yet arrived. Now leave our own galaxy entirely. The Milky Way spans roughly 100,000 light-years. Light crossing from one side to the other takes about 100,000 years. Imagine an astronomer living near the opposite edge of our galaxy with a telescope powerful enough to observe Earth. What would they see? Not our modern civilization, not cities illuminated at night, not satellites orbiting our planet. They would see Earth as it existed roughly 100,000 years ago, long before agriculture, long before written language, long before the first civilizations. From their perspective, humanity would still consist of small populations of hunter-gatherers living through the late Pleistocene. The Roman Empire would not yet exist. Neither would Egypt's pyramids. Even our species was only beginning to spread across the continents. Notice what this means. That ancient Earth hasn't vanished. Its light is still traveling. It is literally crossing the universe at this very moment. Every second, another spherical shell of information from Earth's past expands outward at the speed of light. 1 light-year away, observers could watch events from 1 year ago. 10 light-years away, they would see Earth 10 years in the past. 1,000 light-years away, they would witness medieval history. 65 million light-years away, they would watch the asteroid impact that ended the reign of the non-avian dinosaurs. From even greater distances, Earth itself would disappear because our planet had not yet formed. Go farther still, and even the Sun would no longer exist. Travel far enough and the Milky Way itself gradually changes into a younger galaxy. The farther into space we look, the farther back in cosmic history we travel. Distance has become time. This is not merely a convenient analogy used by astronomers. It is one of the deepest observational facts in cosmology. Every sufficiently powerful telescope is also a time machine, not because it travels through time, because it collects ancient light. In 1995, the Hubble Space Telescope performed an experiment that initially seemed almost foolish. Astronomers pointed Hubble toward a tiny patch of sky that appeared almost completely empty. For nearly 10 consecutive days, the telescope collected every photon arriving from that tiny region. Many scientists wondered whether they were wasting precious observing time. When the image was finally processed, the result stunned the astronomical community. The supposedly empty region contained thousands of galaxies, not stars, entire galaxies, each holding hundreds of billions of stars. Many of them were so distant that their light had been traveling for billions of years before finally reaching Hubble's mirror. Some of those galaxies appeared as they were when the universe was only a small fraction of its current age. It was as though Hubble had uncovered a fossil record of cosmic history written entirely in light. Later, the James Webb Space Telescope pushed this idea further. Using infrared observations, Webb began detecting galaxies whose light has traveled for more than 13 billion years. Some of these galaxies formed only a few 100 million years after the Big Bang, a period often called the cosmic dawn, when the first generations of stars ignited and began transforming the young universe. Every Webb image is therefore more than a beautiful photograph. It is a direct observation of the universe's infancy. When astronomers compare nearby galaxies with these ancient ones, they are not simply comparing different places, they are comparing different eras of cosmic history. Nearby spiral galaxies, like the Milky Way, appear mature, chemically enriched, and dynamically settled. The most distant galaxies often look compact, irregular, and violently active, revealing a universe still assembling its large-scale structure. In a sense, the universe has left behind its own autobiography. Each layer of distance corresponds to another chapter. And that brings us back to our original question. If light from every era of cosmic history is still crossing space, if ancient photons continue carrying information from events billions of years old, if somewhere, unimaginably far away, Earth's distant past is still physically propagating through the cosmos, then in what sense can we truly say that the past has disappeared? Has it vanished, or has it simply moved beyond our immediate reach? This distinction may seem philosophical, but it becomes profoundly physical when we combine these observations with Einstein's spacetime. Because once information, light, and spacetime are considered together, the past begins to look less like something that is gone and more like something that occupies a different region of reality, one that the universe itself has never erased. At this point, you might think we've already answered the question. Perhaps the past still exists because its light is still traveling through space. But that explanation isn't actually enough. Imagine someone asks, if all those ancient photons were somehow absorbed tomorrow, would the past finally disappear? Surprisingly, physics doesn't think the answer is that simple. Because light is not the past. Light is merely information about the past. These are very different things. Suppose every photograph of your childhood suddenly vanished, every video, every written record, every memory. Would your childhood cease to have existed? Of course not. The evidence may disappear. The events themselves either happened or they didn't. Modern physics asks an even stranger question. Could space-time itself permanently contain those events? To understand why many physicists take this possibility seriously, we need to imagine the universe in a completely different way. Forget clocks for a moment. Forget calendars. Forget seconds. Instead, imagine the entire cosmos as a gigantic four-dimensional landscape, not 3 dimensions, 4. Length, width, height, and time. We usually think of ourselves as moving through space while time flows around us. Einstein suggested something much stranger. Perhaps we are always moving through space-time. Every second of your life adds another point to your world line. If someone could somehow step outside space-time itself, an impossible thought experiment, but a useful one, they would not see your life unfolding. They would see your entire existence at once. Your birth, your first word, your last conversation, your final heartbeat, not happening one after another, simply existing at different locations inside space-time. Think about Mount Everest. When a climber reaches the summit, the mountain doesn't suddenly disappear below them. Every lower altitude still exists. The climber simply occupies a different position. Relativity suggests that time may behave similarly. Yesterday isn't destroyed. Tomorrow isn't created. Your conscious experience simply occupies a different location along your world line. This idea feels almost impossible because our brains evolved to experience one moment at a time. Evolution never required us to perceive four-dimensional geometry, it required us to survive. Our experience of now may therefore be less like reality itself and more like a flashlight moving across a map. The map already exists. The flashlight merely illuminates one small region.
Whether that flashlight truly moves, or whether movement itself is an illusion, remains one of the deepest open questions in the philosophy of physics. But relativity introduces another structure that makes this picture even more remarkable. Physicists call them light cones. Every event in spacetime possesses one. Imagine the exact moment you finish speaking a single word. From that event, light begins traveling outward in every direction at exactly the speed of light. 1 second later, that light has formed an expanding sphere almost 300,000 kilometers in radius. 1 year later, that same information occupies an unimaginably vast shell moving through the Milky Way. In another 100 million years, it may pass through another galaxy entirely. Long after Earth itself has changed beyond recognition, those photons will continue traveling. Your words will still exist as tiny disturbances in the electromagnetic field, almost unimaginably weak, but still obeying Maxwell's equations. Now, reverse the picture. Instead of asking where your information goes, ask what information could possibly reach you. Draw another cone extending backward through spacetime. Every photon that has ever reached your eyes, every gravitational influence, every particle capable of affecting you must originate inside this backward-pointing cone. This region is called your past light cone.
Everything outside it is literally incapable of influencing you at this moment. Not because it doesn't exist, because no signal traveling at or below the speed of light has had enough time to arrive. This distinction is absolutely fundamental. Physics does not divide reality into simply past and future. It divides spacetime into regions connected by causality. Events inside your past light cone can influence you. Events inside your future light cone can be influenced by you. Everything else occupies what relativists call space-like separation. These events are neither in your past nor your future. Whether they happen now depends entirely upon the observer. That sentence is easy to hear. It is much harder to truly appreciate. Imagine two supernovae exploding simultaneously in distant galaxies billions of light years apart. Can we honestly say they occurred at the same time? Common sense says yes. Relativity says the question itself has no universal answer. An astronaut traveling at an enormous velocity may calculate that one explosion occurred first. Another observer moving differently concludes the opposite. Neither calculation is wrong. Both follow directly from Einstein's equations. This is one of the reasons so many physicists abandoned the idea of an absolute present. If the present depends on the observer, how can it possess objective physical existence? The British physicist Dennis Sciama once remarked that relativity removed the notion of a universal present from physics. Later, philosopher Hilary Putnam argued that relativity strongly supports the existence of a four-dimensional reality, in which past, present, and future coexist. Even Einstein himself gradually adopted a remarkably similar view. Perhaps the most famous example comes from 1955. Einstein's lifelong friend Michele Besso had died only weeks earlier. While writing to Besso's family, Einstein included a sentence that has become one of the most quoted reflections in the history of science. He wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Notice what he did not say. He did not say time is an illusion. He did not say events are imaginary. He specifically referred to the distinction between past, present, and future. Those words have been interpreted in many different ways over the decades. Some physicists see them as support for the Bloch universe. Others argue Einstein was speaking philosophically rather than making a formal scientific claim. Either way, the sentence reveals just how radically relativity had transformed his own thinking. The man who revolutionized physics no longer regarded the flowing present as fundamental. Instead, he increasingly viewed space-time itself as the enduring reality. And then, general relativity makes the story even stranger, because according to Einstein's 1915 theory, space-time is not merely a passive stage where events unfold.
It is a physical object. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. This elegant summary, later expressed by the physicist John Archibald Wheeler, completely changed our picture of gravity. Gravity is no longer an invisible force pulling objects together across empty space. Instead, massive objects reshape spacetime itself. The Earth follows the curved geometry created by the Sun. The Moon follows the curved geometry created by Earth. Galaxies orbit within the curved geometry generated by trillions of stars and enormous halos of dark matter. Even light, the fastest thing in the universe, cannot escape this geometry. It bends, it curves, it follows the structure of spacetime. Now pause for a moment. If spacetime is a real physical entity, and if your past consists of events embedded within that spacetime, then asking whether yesterday's part of a mountain still exists after you've climbed higher becomes surprisingly similar to asking whether yesterday's part of a mountain still exists after you've climbed higher. The mountain hasn't disappeared, your position has changed. This picture becomes even more compelling when we study the most extreme objects in the universe: black holes. Because near a black hole, spacetime becomes so profoundly distorted that our everyday intuition about time begins to fail completely. Clocks no longer agree. Minutes and years cease to have universal meaning. Observers can witness entirely different realities, while each remains perfectly correct according to Einstein's equations. And astonishingly, inside these cosmic laboratories, physicists have found some of the strongest clues yet that time itself may be far stranger than anyone imagined.
Now, imagine falling toward a black hole. Not because you want to, not because it would be survivable, but because black holes are nature's most extreme experiments. Every law of physics is pushed to its limit there. Gravity becomes so intense that space and time themselves behave in ways that seem almost impossible. Suppose you were carrying the most accurate atomic clock ever built. Far away from the black hole, another identical clock remains safely aboard a distant spacecraft. Both clocks are perfectly synchronized. As you descend toward the black hole, something extraordinary begins to happen. To you, nothing seems unusual. Your heart beats normally, your watch ticks normally, your thoughts unfold exactly as they always have. Local physics never announces that anything strange is happening. But to the distant observer, your clock begins slowing down. At first, only slightly, then more noticeably. As you approach the event horizon, the boundary beyond which not even light can escape, your clock appears to slow almost to a standstill. From their perspective, your movements become increasingly sluggish. The light leaving your spacecraft becomes more and more redshifted. Its energy decreases. Eventually, you become so faint that you fade into darkness. To the distant observer, it appears as though you never quite cross the event horizon. You simply freeze there forever. Yet, from your own perspective, you continue inward without noticing anything particularly special at the horizon itself, assuming the black hole is large enough to avoid extreme tidal forces. How can both descriptions be correct? Because there is no universal clock against which both observers can compare reality. Time has become local. It depends on the geometry of space-time. This is not science fiction. Time dilation has been measured repeatedly. Atomic clocks flown aboard aircraft run at slightly different rates than identical clocks on Earth. The global positioning system corrects for both special and general relativity every single day. Without Einstein's equations, GPS would accumulate errors of several kilometers within a single day. Every time your phone calculates your position, it quietly confirms that time is not universal. The same phenomenon becomes dramatically amplified near neutron stars and black holes. Gravity does not merely pull objects, it reshapes the flow of time itself. And this leads to one of the deepest paradoxes in modern theoretical physics.
Imagine watching someone fall into a black hole. From your viewpoint, they never seem to disappear completely. Information about them appears to remain spread across the event horizon. Yet from their own perspective, they continue inward. Where then is the event actually located? Does it remain outside forever? Or has it already happened? This puzzle eventually evolved into one of the greatest unsolved problems in science, the black hole information paradox. In the 1970s, Stephen Hawking made an astonishing discovery. Combining quantum field theory with curved spacetime, he showed that black holes are not perfectly black. They slowly emit what is now called Hawking radiation. Over unimaginable lengths of time, black holes can gradually evaporate. At first, this seemed to create a disaster. If a black hole eventually disappears, what happens to all the information describing everything that ever fell into it?
Quantum mechanics insists that information cannot simply vanish. General relativity seemed to suggest that it could. For decades, these two great pillars of modern physics appeared to contradict one another. Some of the greatest minds in theoretical physics, including Stephen Hawking, Leonard Susskind, Gerard 't Hooft, Juan Maldacena, and many others, spent decades debating this single question. Remarkably, Hawking himself eventually changed his position. He came to accept that information is probably not destroyed after all. Exactly how it survives remains an active area of research. This matters because it tells us something profound. Modern physics increasingly treats information as fundamental. Some physicists have even suggested that space-time itself may emerge from patterns of quantum information. If that idea proves correct, then the distinction between events and records of events may be far subtler than we currently imagine. And suddenly, our original question returns yet again. If information is never fundamentally destroyed, could the past ever truly disappear? Some physicists believe the answer is no. Not because the past remains accessible, not because we can travel back to it, but because every interaction leaves traces woven into the quantum state of the universe. The photons leaving distant galaxies, the neutrinos passing silently through planets, the gravitational waves rippling across spacetime, even the slight gravitational influence every object exerts on every other object. The universe is constantly recording itself. Of course, recording is not the same as remembering. Quantum information becomes dispersed, entangled, practically unrecoverable. Yet, according to the mathematics, it may never be completely erased. This brings us to an extraordinary realization. Throughout this journey, we began with what seemed like a simple question: does the past still exist? At first, it sounded almost philosophical. Then, astronomy transformed the question. Every telescope became a machine for looking backward through time. Relativity transformed it again. The present itself dissolved into something observer-dependent. Thermodynamics introduced the arrow of time, not as a fundamental law, but as a statistical consequence of an extraordinarily ordered beginning. Black holes taught us that information may be preserved even when our intuition insists it should be lost. One by one, the assumptions we inherited from everyday life began to fall away. And yet, despite more than a century of extraordinary progress, physics has never reached a final answer. Some researchers support the block universe, in which every event, past, present, and future, is equally real within four-dimensional spacetime. Others argue that the present possesses a unique physical status that our current theories simply fail to capture. Approaches to quantum gravity differ dramatically. Loop quantum gravity suggests space-time itself may be quantized. Some interpretations of quantum mechanics hint that the flow of time may emerge from entanglement. The Wheeler-DeWitt equation, one of the earliest attempts to quantize gravity, contains no explicit time variable at all, leading some physicists to ask whether time is something that emerges rather than something fundamental. Even today, there is no consensus. Perhaps the greatest lesson is not that we have solved the mystery, it is that the mystery became deeper the more carefully we investigated it.
The child who asks where yesterday went is asking a question that still echoes through the world's leading research institutes. The same question appears in conferences on quantum gravity, in debates over the foundations of cosmology, in studies of black holes, in attempts to reconcile general relativity with quantum mechanics. The universe has answered many of humanity's questions, but this one, it still whispers instead of speaking. So, does the past still exist? If by exist we mean that we can return to it, probably not.
Every known law of physics places strict limits on traveling into our own past. If by exists we mean that its information continues propagating through the universe, the answer appears to be yes. Ancient light still crosses intergalactic space. Gravitational waves continue expanding across the cosmos. Every distant galaxy is carrying another fragment of cosmic history. And if by exists we mean that past events remain embedded within the four-dimensional structure of space-time itself, Einstein's relativity suggests an answer that is as beautiful as it is unsettling. Perhaps yesterday has never gone anywhere. Perhaps it occupies exactly the place where it always has, not behind us, but elsewhere in space-time. Whether that picture is ultimately correct is something future physics must decide. But until then, every time you look into the night sky, remember this. You are not simply looking across space. You are looking across history. The stars are not merely distant, they are ancient. The galaxies are not just far away, they are chapters from a story still arriving. And perhaps the greatest mystery is not whether the past still exists, but whether the universe has ever truly allowed anything to disappear at all.